What is Euler's formula and Moivre's formula? And let's discuss geometry and linear order in the complex plane. Hello everyone. First, Euler's formula says that e to the I theta equals cos theta plus I sine theta. There are a few handy results of this. First, setting theta equal to pi, we get e to the I pi equals cos pi plus I sine pi, which is equal to -1. Hence, we get e to the I pi plus 1 equals 0. Also, squaring Euler's formula, we get e to the I theta squared equals cos theta plus I sine theta all squared, i.e. e to the I 2 theta equals cos squared theta minus sine squared theta plus 2i sine theta cos theta. But from Euler's formula, we have e to the I 2 theta equals cos 2 theta plus I sine 2 theta. As the real and imaginary parts need to be equal, we have that cos 2 theta equals cos squared theta minus sine squared theta, and sine 2 theta equals 2 sine theta cos theta. We also have de Moivre's formula, which says that the nth root of z equals the nth root of r times e to the I theta, which is equal to the nth root of r times e to the I in brackets theta plus 2 pi k all over n, or k equals 0 up to k equals n minus 1. Thus we have that the roots will form a regular n-sided polygon. Now let's move on to geometry in the complex plane. Circles are given by the equation the modulus of z minus a equals r, where a is a complex number that is the centre of the circle and r is greater than 0 and is the radius. If b is a complex number not equal to 0, then the line through the origin in the direction of b is the set of all points of the form TB, where t is a real number. An equation of a line passing through the points z1 and z2 in the complex plane is z equals z1 plus t times z2 minus z1, where again t is some real number. Where a and b are complex numbers with b not equal to 0, the equation of a half plane determined by the line through a parallel to b and in the direction to the left of b is equal to this set here. Now, let's discuss linear order. A linear order on a set x is a binary operation less than or equal on x such that it follows the following 4 criteria. First, for all x and y in x, exactly one of these holds. X is less than y, x is equal to y, or x is greater than y. Secondly, the binary operation needs to be transitive, i.e. for all x, y and z in x, if x is less than or equal to y and y is less than or equal to z, then x is less than or equal to z. Thirdly, we have that for any x in x, x should be less than or equal to itself. Fourthly, if x is less than or equal to y and y is less than or equal to x, then x equals y. Now, let's show there is no linear order on the complex planes that extends from the linear order on the real numbers. For a linear order extending from the real numbers, say less than star, it will have condition A that for all x and y in the complex numbers, if 0 is less than star x and 0 is less than star y, then 0 is less than star xy. And we have condition B that for all x in the complex numbers, 0 is less than star x if and only if minus x is less than star 0. For a contradiction, let's assume such a linear order exists. By the definition of a linear order, we must have that exactly one of these holds. 0 is less than star I, 0 is equal to I, or I is less than star 0. Clearly, 0 does not equal I, so that case does not hold. Now, let's consider the case where 0 is less than star I. Then 0 would be less than star I dot I, which is equal to -1, by condition A, which implies that 0 is less than star -1 times -1, which equals 1, again by A. But this implies that -1 is less than star 0 by B. So we have that 0 is less than star -1 and -1 is less than star 0, which contradicts the definition of being a linear order. Thus, by the definition of linear order, we must have that I is less than star 0, so 0 is less than star r minus I by b. But then 0 is less than star minus I times minus I, which is equal to minus 1, again by a. Thus, again, we reach a contradiction as in the previous case. This contradiction means there's no linear order on the complex numbers that extends from the real numbers.
As ever, thank you for watching.